There we go. Oops. It's okay. 130 minutes. Okay, I can't do it. I thought I could do a poll, but I don't know where it is anymore. So, does it shift to the left or to the right? Yeah, so to the left. That's correct. Good. So it shifts to the left, right? That means it shifts towards the solid state, right? The aqueous state, not the aqueous state, or away from the aqueous state. So if it shifts to the left towards the solid state, does that mean you're dissolving less solid or more solid? If you're shifting it towards the solid. Yeah, dissolving less. Exactly. So having the common ion, right, in the water is just, it's really just a principle, or really just an extension of Le Chatelier's principle. So you have an ion, it shifts it towards the solid, so it dissolves less, right? The rightward reaction doesn't happen as much, or the dissolution. Good. Does that clear it up? Any other questions on that?
Wait, sorry. So I had a question on this.
Yeah.
So for the second part of just water, would the equation be H2O plus the silver ion?
For the second equation with just water, usually you don't um, put in the what's the word? Not solute, solvent. Yeah. So you usually don't put in the solvent in the dissociation equation. So you would just say like this one's within a solute. So if you were to set up like an ice table, really the only difference numerically between these would be like, and let me write two of these. AG, I'm going to do it on the right since I have a lot of screen space. AgCl. So like if they were to ask you to do an ice table, and you could actually solve this, right? If I gave you the KSP, you don't have to because that would take forever. But if you set up an ice table like this, we don't care about the solid. The starting concentration for the first solution would just be like, let's say that's 0.5 molar, would be something like that. And then these would just be zero. So you don't add the water. It just means that you don't start with any of the ion.
Okay, I got it. Thank you.
Mhm. And the reason why too is if you do add water, it doesn't do anything. So it just goes away in the net ionic reaction. Good question. Okay, great. And then again, you could work this out, right? You could see how much less it dissolves if I gave you the KSP, but you don't have to, right? If it's just a multiple choice, you can just say it dissolves less, right? Because it shifts to the left. If you want the numbers, right, you can get it. Um, and you'll find that this X is significantly smaller. All right, great. Any other questions on this one? Okay. Oh, just for clarification, but if you mix a weak acid and a strong base, you get the conjugate base and water. Well, if it's the strength of what, so in general, it doesn't really matter. If you're talking about the weak acid, right? Strong base just fully dissolves. Same with a strong acid. You do just get the conjugate base and water. So different ways that that changes. And I should note, right? Depends on how much of a strong base you add. So someone's asking, if you mix a weak acid and a strong base, do you just get the conjugate base and water? The answer is it depends, because if you add enough strong base, that neutralizes all of the weak acids. So the moles are equal, right? This is what you did in your titration at the equivalence point. If you neutralize all of the acid, right, with the strong base, then you're only left with the conjugate base, right, the weak base and water. However, if you don't add the same amount, then you end up with a buffer system. So like let's say if you had half the moles, then you would, so half the moles of like the weak acid, right? And you, let's say you have ten moles of the weak acid, you add 5 moles of the strong base, then you convert 5 of the moles of the weak acid into its conjugate base. Right? You assume that you're not doing any of the funny ice table stuff just to make your life easier, significantly easier. So you assume you don't do any of the funny ice table stuff. You just assume like it's a straight up reaction, right? Fully react. So you're left with a buffer system, which is also why, right, in your labs you see that buffer region, that really large kind of flat region in the titration curves because you make a buffer, right? You make a buffer with the weak acid and the strong base, and then when all of it gets converted, you no longer have a buffer, and then it just shoots up. So yeah, does that clear it up? I can. So I'll do that afterwards since someone else asked a question first. So we'll do the weak acid, strong base after. And then identify Lewis acid base. So I'll do those after since those are in the same. So someone asked, could you do set number 2 in the final Enderly reader number 13? 2 13. It says a civil engineer wants to reduce odors at a wastewater treatment plant by adding hydrogen peroxide to sewage. The hydrogen peroxide is delivered as 50% by mass solution, but for maintenance and safety issues, it's diluted to 3% by mass. That's like what you buy at the store, I think. I think it's 3%. If the engineer needs 20 gallons of the 3% by mass aqueous solution, how many gallons of water does the engineer need to add to the 50% solution? So, oh, and they have different densities. Got it. Does that even matter? Let me think. So the first question is, right, it's a dilution problem. So the first question that I would ask is, can you use M1V1 equals M2V2? Um, I would think so. Oh, it's 50% by mass. So adding water is not the same. Hmm. Does it? I feel like you could finagle it, but maybe that's only percent by volume, um, where it works. Hmm. Okay, so why don't we just start writing down what we have? Right, that's what I would start with. So you start with 20 gallons, or you start with 20 gallons. Um, he needs 20 gallons of the 3% solution. So we know that he needs 20 gallons, or they need 20 gallons. How many gallons of water? Oh, do you guys have the conversion for gallon? Does he give it to you on the cheat sheet? Gallons to milliliters? Yeah, okay. Because I don't know. It says, how many gallons of water does the engineer need to add to the 50% solution? Mm, oh, got it. Wait. But they don't tell you how much. So the thing, what I was thinking of doing, and I think it still works, but it seems like there's something missing, at least for clarity in the question. So I think the plan is you first figure out how much mass of hydrogen peroxide you you have. Yeah, because they don't tell you how much you're using. Hmm, I guess that's the only way that makes sense. Yeah, and I guess it makes sense because it's fixed. So the plan here is to figure out how much mass of hydrogen peroxide do you have in the 20 gallons of the 3% by mass aqueous solution? Why? So if you can figure out how much mass you need, right, of the hydrogen peroxide from the 3% solution, then you can figure out how much of the 50% solution you need. Why are you allowed to do this? Because the mass has to stay the same. If you're just adding water, then all of the mass from the 50% solution is still going to be all the mass you have in the 3%, right? You don't get to add more mass. And you can't add less mass because it has to be 20 gallons. And so the first thing, and you can't add more mass, right? Because it has to be 20 gallons. So you first need to figure out how much mass of hydrogen peroxide you have in the 3%. Then we're going to figure out how much volume of the 50% we need to use. And then we're going to just use the rest with water, right? To get to 20 gallons. Right. And then that's gonna work out. So they're giving us the density. Mm, yeah. So that gives us the mass of the solution, and then it's 50 or 3% of that. So first we have to convert gallons into milliliters. I don't know it. So, and you guys are giving it. So I'm just gonna go ahead and do that. Great. So we know 20 gallons is 75,708.2 milliliters. So now what we can do is figure out how much mass we have in the 3% by mass solution. We have 20 gallons of it, right? So we know that density, we're given densities. Density is equal to mass over volume, right? This is mass of the solution, not mass of hydrogen peroxide. And then the density of the 3% is 1.015 grams per milliliter. I'm just going to leave it at 1.015. The mass we still don't have, right? That's what we want. We want the mass of the solution to get the mass of the hydrogen peroxide. We have 20 gallons, which is 75,708.2. The units are all in milliliters, so this is consistent. I'm not worried about it. You solve for mass here. 1.015 times 75,708.2. So we get the mass to be 7 point, I'm just gonna write this in scientific. 68 times 10 to the fourth grams. Right, that's the mass of the total solution. So if you want the mass of the hydrogen peroxide, you just take a percent, right? It's 3% by mass. So we take that, times it by 0.03, and we get 2.305 times 10 to the negative 10 to the negative 10 to the third grams. That's just that times 3%. Any questions so far from anyone? Okay. Again, the reason we're finding the mass of hydrogen peroxide is because all of it's going to come from the 50% by mass solution. And then we're going to see how much we have to use of that. So then what we can do is take this and uh, do we use this in the 50% by mass solution? Give me a sec. Maybe it's not as clear cut as I thought. So we have oh no, this is right. Yes, we have 2.305 times 10 to the third grams of H2O2 that we need, right, for this solution. So now we have to figure out how much volume of the mass solution of the 50% by mass solution we need. So what we can do is this. We can say that the mass of the 50% solution, because we have the density and we want the volume. So it's going to be mass divided by density, right? Just solving for volume. We need the mass of the solution because we have the density of the solution. How do you get the mass of the solution? Well, it's just this times 2, right? because it's 50% by mass. So if 50% of it is hydrogen peroxide, you just double it and you get the mass. That's grams of the 50% solution. This is quite a tricky problem. And then we can plug it in over here, right, into our volume. So the volume that we're going to use of the 50% solution, this is in milliliters, is 4.611 times 10 to the third grams. I'm just going to leave out the unit. The density is 1.197. And then we get 3.852 times 10 to the third milliliters. So we're almost done here, right? So that's how much volume we need of the original solution, the 50%, to get the correct mass to get a 3% by mass solution of hydrogen peroxide. So now what we can do is convert this back into gallons, or we keep it in milliliters. Does it say? Yeah, it says gallons. So I'm going to convert this back into gallons. This is 3,852. It's about 1.018 gallons. So if we want 20 gallons in total, right, and we use 1.0818 gallons of the original solution of the 50%, then I'm just going to take 20 minus 1.0818, right? And that's the volume that we're using. 20 minus 1.018. So quite a difficult problem, honestly. 1 point, or I'm just going to do it 18.98 gallons. 98. Yeah, I guess 98. Okay. There's no two. Okay, whatever. I'll trust the calculator. But yeah, that's it. So you're gonna add 18.98 gallons to 1.018 gallons with a 50%. So quite a hard problem, honestly, just because you can't use like M1V1 equals M2V2 outright. And it's because the densities are different, but they're linked by the mass, right? So the mass of the H2O2 is the same in both. Any other questions on this? And I'm actually gonna full screen this just because, yeah, not a very fun problem. That's correct. Step by step, simplified on how to approach it. See if we can. So I would say first, see if you can use M1V1 equals M2V2. Um, but I think the problem with that is that the units don't work, right? Because the percent by mass with different densities doesn't really respect the assumptions of that formula. So you'd say, I can't use that. So what's another way I could do this, right? And the only other way that I can think of is the way that you've been doing it in labs, right? Where it's like, if I want this end amount, how many milliliters do I need to add, right? Um, so like, because you guys have been doing that, right? It's like my V2 is going to be 20, my M2 is this, right? So instead of M2, it's mass this time. And then I don't know my V1, right? I need to figure out how much volume of like the HCl or whatever NaOH that I need to get the desired volume and molarity, right? And I give you the initial molarity. So it's like M1 V1, but just with more steps, I guess. But that's the way I would do it, right? I would try to relate it to something that you've already seen before. So you know to get to 20 gallons, you have some amount of the 50%, some amount of the 3%, or of the of water. Um, and you could figure out the amount of the 50%, right, through the mass, percent by mass, just like you would with solutions, right? With moles. You're like, I need this many moles, so I add this amount, or something like that. I don't know if there's a super cut and dry way. Sorry. Yeah, of course. Any other questions on this one? Does M1V1? I don't think it does. Yeah, I just don't think it works because of the different densities. Um, yeah, I just don't see it. Okay, so that's that one. And then the other questions were on the weak acids. So we're talking about mixing a weak acid and a strong base. Can you write down some visual examples? So I guess I can do this with an ice table. So I don't have enough white space. So if you have some, oh, there we go. If you have an acid and you're adding a strong base, I'm just going to pretend that these are aqueous because I don't want to write the NaOH or something like that. Oops, not OChem. Don't circle it. We get a reaction like this. Notice how this is not equilibrium, right? This is not reversible. So you get a reaction like that. So a weak acid with a strong base. So the two examples I noted were it depends on how much you add. So suppose that you have like pretend this ice table is in moles because I think that makes the most sense here to talk about it. So if you have 10 moles of the weak acid, and then you have 10 moles of the hydroxide, and assuming you start with none of these, or the water doesn't matter, then you just do the full reaction, right? You get minus 10, plus 10. And then this ice table isn't just for equilibrium, right? You can think of the E as end, and then this is 0, and this is 0, and that is 10, right? So you can see that all of the weak acid got converted into its conjugate base, right? When the moles of the strong base are equal to the moles of the weak acid, just like you did in lab, right? This is on your titration curve, that was like this point right here when the moles were equal. Then the other example or other thing that I was noting is what if they're not equal? Oh, there we go. So what if instead like this one is 5, right? Then what do? Well, you do the same thing, right? The limiting reactant, this is just a limiting reactant problem, really. That's 5, and then this is 5. Oh, 5 for the second one, not 5. Moving too fast. That's 0. 5, 0, and 5, like that. So looking at this, right, you can see that after the reaction happens, you have your weak acid and you have the conjugate base, right? Because the moles of the weak acid is not the same um, as the strong base that you add, right? There's more moles of the weak acid. And because they're not the same, right, you end up with some of your weak acid and some of your conjugate base. So in your titration curves, that was like this region. Why does it look like that? And why is it called a buffer region? Because you literally make a buffer in there, right? When you add the strong base, you make a buffer system, right? This is the buffer region because you have a buffer system. You have some of your weak acid and some of your conjugate base, which is by definition a buffer system. And so when they're not equal, right, not all of it gets converted into a weak base, just the amount from the hydroxide that you add. And that's it. And then if you add more OH than the weak acid, if you guys get a problem on that, you assume that the conjugate base is it negligibly changes the pH. So you just go based off of like um off of the remaining hydroxide concentration, and that's it. Does that clear it up? So if we did this problem, the log of B over A, in this case, yeah, in this case, the log of B over A is 0. But like if I change this to like 7, right, then then it wouldn't be 0. And but you would do the same thing, but you're correct on this one, right? Then B over A would be like 7 over 3, log of 7 over 3. And so you would use the Henderson-Hasselbalch, and then you could find the pH. But yeah, so that's the only other way that they can make these harder is you add some strong base and then you find the pH just using the Henderson-Hasselbalch, right? Because you made a buffer. Let's see who's left. Not too many. Okay. Um, in a design a buffer, had to add X in the change row. So my question is it possible to subtract X from one reactant and add X? No. Yeah, you'll always be subtracting X on the reactant side. And that's due to conservation of mass. Oh, wait, really? Um, I don't wait. Did they release the answers for exam two? Okay, so I would pull it up, but I don't have a version, and I if I pull up Gradescope, it shows everyone's grades. So, um, but I can take a look afterwards. Just because again, I don't want to show everyone's grades. I don't have a blank slate of the midterm two or the answers. But designing a buffer, I don't know. Like, did they start you with some weak acid or weak base, and then you added like an acid or a base to convert it? Is that what they did? It was like polyprotic. So it's H2PO4, and they add OH for the X. Multiple solutions, and they give you the Ka and pKa. Got it. So I think you guys might be talking about different ones. So there's buffer problems where you just pick the buffer with the closest pKa. Um, and they give you the initial amount. Oh, got it. Yes, it still should be minus X. That might have been a mistake on the answer key. Because if you were to use this in the Henderson-Hasselbalch, um, and then added X to 0, maybe it's a way to make it they subtract it from the 1.08. Yeah, I think they have a notation error. Maybe the math works out, but you're not you're not really allowed to do that. You can start with some random amount and then subtract off like some amount X or Y or whatever. But on the reactant side, you can't add and to to the reactants. Yeah, that just violates the conservation of mass. So I think maybe their math works out, probably, right? But Because I don't think Enderley wrote the ans in the Henderson Hasselbeck 1.08. Oh yeah. So after the mod, so I'm not sure. So if you have a polyprotic acid, let's just pretend AH is polyprotic. That's cursive. Um, like this, right? And you're saying that you start with was it 1.08, and then this was 0.72, like that. Yeah, NOH is 0. And they put a plus X here. Yeah, no, they made a mistake. That's wrong. This is supposed to be X amount that you don't know, and this is minus X. And then it goes to 0 down here, right, where it all gets used up. So then this is still 1.08 minus X. This is 1.08 minus X. That's plus X. That's 0.72 plus X. And this is still consistent with the Henderson-Hasselbalch. So they just made a mistake here. That's wrong. You should start with X amount that you don't know, and you assume all of it gets used up. Yeah. So they made a mistake, whoever wrote it. And then it says to find the milliliters of 6 molar NaOH to get the buffer. So how would I find that milliliters? Um, is this before mixing? Like, are these the initial concentrations, or are they just in a solution? Those are the numbers after Stoic was done. It's not. So what I'm asking is, do are the acid and the conjugate base already mixed, or is this before mixing? Because then that complicates it a lot more. Okay, so they were already mixed, and then you have the X here. Um, yeah, that's a lot harder. So once you solve for X, because this table is in molarity, I'm assuming this is in molarity. And you drop the volume. Mm, no. Yeah, so they give you the pH. So they basically just give you everything that you need to solve for the X. Let's see. If X is in molarity, you don't, so you have molarity. If you want volume, that means that you either need, well, that means you need the mass. So that means you need the mass, you need the moles. You need the moles of NaOH you need. So did they give you the total volume of the solution? Yeah, 'cause I think there's something that's missing. And again, I would pull it, I just can't because it shows everyone's grades. But if you want to convert molarity into volume, you need moles. So what I would probably do, it was 400 milliliters for the 1.8 molar. Yeah, so then I would actually not do this table in molarity, just to, I mean, because I'm having a hard time just conceptualizing it with molarity. I would instead convert this table to moles. Do they give you the molarity of the OH that you have? Oh, wait, but it's OH in the volume. So I guess you could. Oh, that's so weird. Yeah, so I'm thinking of it, I think no. So you can do what we did here. There's two ways you can do it. I'm thinking of it in a way where I'm adding some amount of moles, and then it just conceptually makes more sense to back calculate it. The way that they're doing this solution is that you're pretending that you add some OH. And I need to ask one more question. Is this 1.08 before or after mixing the OH in? After. Okay, great. So it's after everything is mixed, so not just the acid and the base. Okay, because I'm gonna say then there might be another problem. So what they're pretending here is like you add some hydroxide with some molarity, and then it dilutes, and then basically nothing is happening, and then all of a sudden it reacts, right? That's kind of how the math is working here. So you start with some initial amount, it all reacts suddenly, and then you get X. So what is X? X is molarity, right? But specifically, X is M2, right, in your dilution formula, because you start with some amount of hydroxide and some molarity, and then after you mix everything, it gets diluted. So your X here is M2. Got it. So the pH increased. Okay. Yeah, so X is your M2. And then what you can do is just use your dilution formula. So you get V1, M1, M2, V2, right? M2 is your X. You have the total volume, and you should have the initial molarity. Otherwise, I have no idea how you would do it. So you can just use the dilution formula. This is a really odd way of doing it. I always work with moles, but it still works. With the screen sharing off. I can, but does this here? So let me give me one sec. Because I know there was another question too. Just give me one sec. Oh, it was the Lewis acid Lewis base. So as I'm pulling this up, I'm just going to quickly describe Lewis acid and Lewis base. Lewis acids and bases are defined on lone pairs. So a Lewis base will donate a lone pair, and a Lewis acid accepts a lone pair. Um, the way you can kind of tell the difference between the two is pick the one with more lone pairs on it. So if it doesn't have four bonds, assume it has lone pairs. If it has more than four bonds, assume it doesn't have any. So if it's like sulfur with a whole bunch of stuff on it, but if you have like oxygen with just two things, assume there's lone pairs on it. It does have lone pairs. Um, but you guys don't know Lewis structures, and so that makes it hard to describe it. Does that clear up the Lewis acid Lewis base? So if it has less than four bonds, assume it has lone pairs. If it has four or more, assume it doesn't have any. And the one that has lone pairs is going to be the Lewis base, right? It's the one that donates the lone pairs. Exam two. I just gotta pick a random person, I guess. Um, which question on the midterm was it? 23B. Phosphate buffers are commonly used in biological systems. In part A, they mix 400 milliliters of 1.8 um, and that many grams of the conjugate acid. So they're just, yeah. Okay, so you can just convert that into moles. Um, and then get the molarity. In part B, the resulting solution is then adjusted to the desired pH with 6.00 NaOH. A, calculate the initial pH of the buffer solution before the addition of the NaOH. So before you add it, you just use the Henderson-Hasselbalch Um, yeah, so that's fine. And then determine the amount in milliliters of the 6 mole. So you do have the initial molarity. Yeah, so it's just 6. So like once you do get the X from that table, you just do M1 V1 equals M2 V2, where the X value that you get, that's the concentration of hydroxide after mixing. So again, you're kind of pretending that it doesn't react for a little bit, and then all of a sudden it just happens at once. And then your M1 is just 6, and then your V2 is just um mm. So then I guess one other thing that you have to consider is that V2, because you're adding some amount, V2 ends up being V1 plus 400, right? Because you start with 400 and then you're adding some amount of hydroxide. So far, so good. Any question? Okay. I don't see anything. It wasn't in the key. So there's multiple ways to do it because I would do this with moles. I wouldn't do it with M1 V1. I would do this a different way, but there's multiple ways you can do it. Because it should work out to be the same. And so you get 6, and I don't have the key either on Gradescope. I only have access to like the student stuff if there's a key on Gradescope. Answer is 6. So let's work this out. Let's see what we get. Because I don't have X either. Well, I guess I have to start from the beginning then. So um I'll start with the acid. Because then what you can do is just algebraically solve for V1. We're saying that gets converted into the conjugate base plus water, like that. That's a liquid. We do the ice table. We're saying we start with some amount of hydroxide that we don't know after mixing. Um, this is 1.08. Just going to assume that the math, wait, yeah, the math is fine. And then, wait, how 400 milliliters? Because I thought it was 1.08. They got 1.08 here. Is that the moles? Are they working in moles? 0 0.4 times 1.8. No. Oh wait, 0.72. Oh, so this is moles. So they're doing this table in moles instead of molarity. So both work. I thought, okay, that's my bad. I thought this was in molarity. So you start with some moles of hydroxide. We're going to add some moles of hydroxide, right? That's really what this is. And then so this whole table is in moles. That's 0.72. That's 1.08. So this is, yeah, so this is the way I would do it. Okay. You get 1.08 minus X, and then 0.72 plus X. That's 1.08 minus X. That's 0. 0.72 plus X. Great. Then we can go ahead and use the Henderson-Hasselbalch equation. So we have the pH that we want. We already have the pKa. It's just the pK of the acid of this buffer, the two conjugates. And then we have log, and this is 0.72 plus x. You're allowed to work in moles here. 0.08 minus x because it's in concentrations, but since they're mixed, right, the molarity is moles divided by volume. The volumes are the same. They end up canceling. So you're allowed to work in moles here. And then you just solve for x. So, oops, I should get rid of this log. I already did the 10 to the power. My bad. So then we just solve for x. So we get 1.08 minus x times 10 to the pH minus pKa, 0.72 plus. Why is it not zero with but x? So I don't know why they add an x here. That just doesn't really make any sense to me because you won't end with x either, right? You add some amount of hydroxide and then it disappears, right? That's how it actually happens. And so what we're saying is, and this is not concentration, right? This is in moles. So we're saying that the moles of hydroxide, we're going to add some amount. I don't know how much we're adding, right? But we're going to start with some, we're going to add some. That's what we start with. Then it does the reaction. We lose all of it, and it converts some of the acid into the base, right? Which is these two last ones. Plus X just conceptually doesn't make sense with the ice table, in my opinion. And so I think it makes sense to start with some amount. You add some amount, right? That's what you're starting with. Then the reaction happens. That's the change part. And you lose all of it, right? And it converts the acid, weak acid into the conjugate base. So we just don't know how much we're adding, right? How many moles of it we're adding, which is why it's X. That's correct. Yeah, we don't know how many moles of NaOH we're adding. And so once we find the moles of NaOH, right, then we convert this into volume because we have the molarity. And so that actually makes this a lot easier conceptually too. Great. So then this is 1.08 minus x, 10 to the pH minus pKa, 0.72 plus, oops, should have it like that, plus x. To solve for x here, let's see. So this is 1.08 times 10 to the pH minus pKa. You subtract 0.72 on both sides. And then we can add the x times 10 to the pH minus pK. Give me 1 sec. I just have to really run to the restroom. Just give me 1 minute. All right, back. Sorry. So excuse me. So what we do now, right? So this part I just got from algebra, right? Just distribute the 10 to the pH minus pK to both. That's where you get the 1.08. And then subtract the 7.2, 0.72. And we also have minus x times 10 to the pH minus pKa. So we add that to both sides, right? And it ends up here. Then you can just factor the x. 1 plus, oh yeah. So I think I worked on this in office hours and I got the exact same thing. Or at least it looks very similar form-wise. Minus pKa 0.72. Yeah, because there's like a 1 to the pH minus pK. And then what we do is to just divide by the 1 plus 10 to the pH minus pKa. So we get 1.08 times 10 to the pH minus pKa minus 0.72 over 1 plus 10 to the pH minus pKa. That's equal to x. Any questions so far? For the change row, did you mean to just put negative x? Yes, sorry, you're right. No, that should just be minus x. That's absolutely right. Oopsies. You're correct. Thank you. Any other questions? Great. Okay, so I'm going to assume no. And so we get X, which is the moles of NaOH, right? So I'm just going to plug in my calculator. So the pH, um, the pH is what? 7.4. So we have 1.08 times 10 to the 7.4 minus the pKa. So it's negative log of, let's see. So the should be working with Ka2. Negative log of 6.3 times 10 to the negative eighth. And then minus 0.72 over 1 plus, and then same thing, 10 to the 7.4 minus negative log 6.3 e to the negative 8. Let me just double check. Yeah, it's Ka2. You assume all of it's used up. So that's an assumption you make. You assume that whenever you add strong base or strong acid, right, to some buffer system, or right, if it's just like a weak acid or whatever, you assume all of it gets used up, unless it's an excess. But it's an assumption you make. You just have to assume all of it gets used up, that it's an irreversible reaction. Right? Technically, it's not because you probably have some stuff floating around from autoionization, but you just assume it does get used up. Good question. So this is 3.386. And this is the moles of OH minus, right, that we need to add since the table was in moles. And then all we should have to do is convert this into volume, right? So if we start with 6 molar, we have 0.386 over the volume. And then we get 0.386 over 6, oops, equals the volume. And then we're left with 0.0638 liters, which is your 64 milliliters. And then that's it. So that feels better doing it in moles. The M1V1 still works. I thought that's what they were doing. It just kind of doesn't make sense conceptually, but it still works fine. Any other questions on this one? Yeah, of course. The hardest part people usually have is the algebra. So I would say try to review that the most if you get stuck on these. Um, like distributing the 10 and then just factoring it out. So you'll see that a lot if you take calculus when you do implicit differentiation. You like add and then factor or distribute then factor, I mean. Okay, great. So I think that's it for this one. And then I see someone else says problem 70 on page 132. So let's see on the reader. I'm not sure if I have access to the reader. Let me close a grade scope. Um, this one, maybe reader. Nope. Uh, lecture. Still get time. Section two. Which one? 132. 70? I'm not sure oh, practice final. So the one on Canvas? Like this one? Oh, wait. Like this one? The worksheet? No, that one was for two. Uh, Chemistry 2A practice exams. There's a wait. Isn't there a bunch? Which one? Which set is it? Oh, it's on page 132. And these are all sequential pages. Got it. So, oh wait, I'm going to go backwards from this. Okay. So 70. 70 says equal volumes of the zinc solution and an NH3 solution are mixed. Kf for that complex ion is 4.1 times 10 to the eighth. It's pretty high. It says if enough sodium oxalate is added to make the solution zero point 0.1 molar in oxalate, will zinc ZnC2O4 precipitate? Sure. So, right, this is kind of a combined reaction, right? So the first thing that you have to do is, so to find whether or not it precipitates, you have to figure out whether Q is less than KSP or greater than or equal to, right? From what we talked about before. Now, how do you get Q? Well, Q is the amount that you have right now. And so we have to figure out how much zinc and NH3 we have right now based off of this other equilibrium reaction. Because I'm going to assume that you mix them, right? And then some of it gets converted into the other ion, right? It's a complex ion. And then you're going to be left with some amount of zinc and some amount of NH3. Now the oxalate doesn't really, it does nothing happens in this first one, but it does affect the amount of zinc, right? So to find the Q of zinc oxalate, we need oxalate concentration and zinc concentration. So what we're going to do is find the zinc concentration um, through not KSP, but through KF. So you know that KF for this formation is going to be the product, right? The complex ion. You can write up the formula too. over the reactants. I'll actually write it out in a sec. Otherwise, you might miss that this is to the fourth power. So we have zinc, we have NH3, and then equilibrium. We have Zn NH3 form, right? Like that, but with brackets and that. All right. So this is not balanced, right? This has to be a 4. So that's the thing you might miss. I would write out the reaction, right? Just to make sure you don't miss it. So then we can, I mean, we're gonna have to write an ice table anyways. So we have an ice table. We start with this 2.02 molar for zinc. So this is gonna be an ice table in molarity. We start with 2 molar for NH3, and we're assuming we start with none of the zinc, right? We do the change, we get minus x minus 4x plus x, and this is now 0.02 minus x. This is 2 minus 4x, and then this is x. Now, we're not going to use the assumption here. I think you might try. I mean, maybe it works, but I'm actually not going to use the assumption here. When we plug into KF, and oh wait, no, you kind of have to. It's gonna get really, yeah, no, it's gonna get too ugly. So we're gonna use the assumption. Otherwise, you can't do this. You're gonna end up with like a quintic formula, a quintic polynomial that you just can't solve. So we start with this. That's our zinc, 2 minus 4x. But I feel like x is going to be pretty large. So this doesn't feel right. But we make the assumption, right, that x is much smaller than both of those, than 0.02. So this ends up just being, uh, is it? I mean, if you make the assumption for just the 2 minus 4x, it's fine. But I don't know if it's going to be fine if we do the 0.02. I guess let's try it. So let's assume that x is much smaller than both of these, just to make life easy. What's KF? 4.1 times 10 to the 8th. And then you solve for x, right? Just multiply. One, that's certainly not right. Uh, did I reverse this? No. Yeah, basically all of it's gonna get used up. Yeah. Oh, I know what I did. Oh, that makes it even worse. This is 2 to the 4th. Um, hmm, let me think. I might let me double check. I'm pretty sure KF is where you add the t to its formation. Unless I'm wrong and reversed it, but that doesn't seem right. No, that's right. You add two things and then you get another thing. Hmm. All right, well, let's try the other way, and then we'll see if that doesn't work. Because if that doesn't work, then I don't know how to do this. So let's not use the assumption for both of these, I guess. Yeah, what I 2 molar feels like something's wrong here, but let's just use the assumption for the 2. 2 minus 4x. Otherwise, you just can't solve it. It's not going to be a quadratic equation anymore. So that's 2 to the fourth. And then I guess we just solve for x now. So this is quadratic. That's if we multiply both sides by the bottom here, we get 4.1 e to the eighth times 16. That's 2 to the fourth. So we're left with 0.02 minus x equals times 6.56 times 10 to the ninth equals x. Now you can solve this just using the quadratic equation, right? Move. Oh wait, no, you could just factor it. I don't really. No, it's not a big deal. I was gonna say I don't really want to solve for quadratic. It's not quadratic. Oops. So then what you can do is just solve for x. This is gonna be 0.02 times the 6.56 times 10 to the ninth. And then we get x plus x times 6.56 times 10 to the ninth, right? Just distribute the 6.56 and then add the x to both sides, right? The negative x times 6.56 times 10 to the ninth. And then you factor the x out. Let's see if this is any better. 0.02 times that divided by 1 plus 6.56 e to the ninth. I mean, it's much better, but now that kind of raises another question. So that gives us 0.02. And if x is 0.02, that means all the zinc gets used up, right? Because zinc, it's 0.02 minus x, which means that the Q for the ZnC2O4 is going to be 0, but that's not an answer here. So, oh, oh, I missed that, didn't I? I missed it. I mean, does that really change that much? So the thing I missed here is it says equal volumes. I thought they were already mixed. My bad. So if these are equal volumes, all you have to have these, right? Because when you mix them, the volumes are going to get halved. But I think it's still going to end up being the same. Yeah. So you would divide both molarities by 2. That's a 1. That's a 1. But I don't know how much it's really going to change. Then that's 1. 1. That's still just 4.1 times 10 to the eighth. 1. I think this is still going to be kind of off. Maybe not. Let's see. 0.01 times 4.1 e to the eighth over 1 plus 4.1 e to the eighth. No, now it's fine. Yeah, so that's the part I missed. So this ends up being 0.0099 and it's repeating. I'm just gonna leave it 999. Well, that's still almost like 0, but um Yeah, I guess it still ends up working out. So if you subtract this from 0.01, 0.01 minus that, you get 2.4 times 10 to the negative 11 for the amount of zinc left. So you get the amount of zinc left to be that, right? This is that 0.01 minus x. And then you can plug that into Q. So it looks like this is going to work out now. So the Q for the KSP here is just the zinc concentration times the oxalate concentration. And then we just compare it to KSP. So let's see, 2.4 times 10 to the negative 11 times 0.1, and that's going to be 2.4 times 10 to the negative 12. So it should be C. I know they got 2.9. Maybe I just plugged in something wrong, but they're close enough. They're the same order of magnitude, right? Same 10 to the negative value. So you can see that Q is much less than K. So the reaction does not shift to the left towards the solid, like we were talking about before. Then the ice table, sulfur X. Yeah, that's correct. Well, you don't plug, yeah, so you plug X back in to find zinc, and then you have to use the Q for the KSP, right? Because these are different. Because you're using NH3 for one of them and you're using oxalate for the other. So you find the concentration of zinc, and then you plug that into the Q for zinc oxalate. Any other questions? You can tell which of the salts. Is there a certain question? Like a particular one that does that problem, or just in general? Because typically, on page 140. Let's see. 140. All good. Question one. Oh, yeah. So you can look to see. So, well, first, you should ask yourself, what does lowering the pH do? It increases the hydrogen concentration. So, do any of these, and as we talked about before with solubility, right? Really, solubility is just Le Chatelier's principle, right? More soluble means that the reaction shifts to the right under certain conditions. Less soluble means it shifts to the left. So, which one of these react with hydrogen, basically? Which one of the conjugate, like if these were to fully dissolve, right? If you were to write these, CaCO3, Ca2 plus, CO3 2 minus, Ba3, PO4 2. I think barium is a 2 plus. And then AgBr, uh, Ag plus Pr minus. So if you were to look at these reactions, right, you would ask yourself, does hydrogen react with any of the products? Why does that matter? Because if it does, by Le Chatelier's principle, if you remove a product, then it pushes the reaction to the right, which makes it more soluble. Or you could also ask, does lowering the pH add a product here in this case, none of them have an H, right, as a product, which would lower the solubility, but um, yeah. So this is just Le Chatelier's principle. So if you were to do this, you would, I think from your solubility rules, or maybe you just have to have it memorized, carbonic acid, HCO3 or H2CO3 is a weak acid. So it will react, right? You have the conjugate base. Um, and so this first one gets shifted to the right because the hydrogen reacts with the CO3 minus and it reacts with this PO4 because in H3PO4, the only strong acid, acidic proton, is the first one. And so 3 minus is just, it's just basic. It's going to react with an H plus. So it would be 1 and 2. And then HBr does not, right? Because the Br minus doesn't react with hydrogen because HBr is a strong acid. So it fully dissolves, right? It's not going to reform. Great. Any other questions? Sure. Lab procedures and setups. Um, huh. So what about them? Flasks and procedures, just in case he asks. I would. I would be familiar with it. I mean, they're not too bad. All right, great. Um, all right, well, I guess if that's it, then best of luck with finals and studying. And then I think I proctor. So then I guess I'll see you on Thursday. All right, have a good one.